So this is joint work between Naama, Mark, and myself from the Technion. So distributed systems must be resilient to failures, and we differentiate between two types of failures. The first type, processes just crash, so they stop operating. But in the second type of failures, which are more difficult to address, processes continue execution, but they act arbitrarily due to bugs or malicious attacks. In a client-server setup, client sends the request to a server, which responds back with an answer. And obviously, when a service is deployed on a single server and that server fails, the whole service becomes unavailable. To mitigate that and provide high availability, the standard approach is to use state machine replication. In state machine replication, the service is replicated across many servers, and then even if some of the servers fails, still the service is available to clients. And the main idea behind that is to use a consensus protocol that allows the servers to agree on the order of client requests and thus achieve a consistent state. So the goal of SMR is to mask server failures for high availability, but that comes at the cost of the consensus overhead in normal execution, even when there is no failures. So consensus protocols that can tolerate Byzantine failures are more robust than protocols that can only tolerate crash failures, but they're also more expensive. They usually need more replicas, 3f+1 instead of the usual 2f+1 replicas. They often rely on signatures or other means of cryptography. And they also need more communication rounds to commit a message. So one line of work that tries to speed up BFT uses trusted components. And these are a piece of hardware that can execute small programs or maintain limited state outside the control of the attacker. And just to give you a few examples, that could be a smart NIC, a trusted execution environment, or sticky bits in memory. And the common idea behind these protocols is to eliminate equivocation, meaning eliminate the ability of a Byzantine replica to send contradicting messages to others. This provides higher fault tolerance, but in general, all these protocols still relies on signatures and still need high communication when some replicas are faulty. So in this work, we propose another trusted component, which is a switch. And unlike the other components, it is not local to any replica, but it is a centralized component that is already within the system. Programmable switch is an appealing component because it sees all the messages of the protocol, it knows the source of a message, and it can also execute some computation per packet. But of course, the main question is it reasonable to trust a switch? So it turns out that many BFT protocols already implicitly trust the switch because they send out unsigned messages and assume that they'll be delivered without being modified. But also, the switches are only programmable through control plane, and usually the control plane is isolated from the network that delivers the packets of users because it sits in a completely different network. In addition to that, switch vendors can lock the switch, so even if an attacker does get access to control plane, it cannot change the behavior of the switch. So the question is, how can we use these trusted switches to improve BFTs? So in this talk, I'm going to show you that trusted programmable switches can not only improve the performance of BFT, but they can also improve the fault tolerance of BFT protocols. I'll begin by showing you what programmable switches can and cannot do. I'll then describe the protocol SwitchBFT that we propose in this paper, and finally I'll show you some performance numbers. So initially, you might think that having a centralized trusted component is going to make this problem completely trivial. The most straightforward approach would be to have the switch sequence client messages and then distribute them to all servers. This, of course, works until some messages get lost in the network. In that case, we need a switch to retransmit the lost messages to the servers. However, programmable switches are memory constrained and they cannot store entire messages for them to be retransmitted later by the switch. So this would not work. Another approach may be to have the switch sign messages. So instead of the switch retransmitting them when they are lost in the network, a server may ask another server to recover a message, and by using the signature, it can verify the authenticity of that message. However, a switch is not only memory limited, but it's also compute limited, and having the switch sign messages is impractical. So what can a trusted switch do for us? So in SwitchBFT, the trusted switch is doing the following. First, it authenticates the source of a packet, but instead of relying on cryptography, we rely on network links, meaning that when a packet comes in and it comes in a specific ingress port, it is obvious to the switch that the source of this packet has to be the physical server that is directly connected to that port. In addition, the trusted switch sequences client messages, so that enables SwitchBFT to commit messages in a single round trip in a fast path without any cross-replica talk. And finally, the switch ensures safety via protocol verification, which enables SwitchBFT to deliver robust performance even if some replicas are faulty. Overall, SwitchBFT provides the same performance and the same fault tolerance as CFT protocols without using signatures at all and without using cryptography on the switch. So we have pretty standard assumptions regarding the network. We assume the network is partially synchronous and it's lossy, so messages can get lost in the network. While we assume that trusted switch is not Byzantine, it may fail by crashing. We assume any number of Byzantine clients and 2f+1 servers, where up to f of them being Byzantine, which is the optimal number of servers to achieve consensus. So the SwitchBFT protocol is comprised of two sub-protocols. The first protocol ensures that messages arrive in the correct order to all servers with possible gaps. And then the second protocol tries to fill that gaps as they happen. So we introduce a new primitive we call verifiable unreliable atomic broadcast, which satisfies the following properties. In executions without packet loss, it guarantees exactly once delivery. For every client message, either all servers receive the message or the receive bottom. All servers receive messages in the same order. And finally, servers can verify that the message is indeed the kth message using a function we call verify. So how does this protocol work? When a client wants to broadcast a message, it computes a digest of the message and sends both the message and the digest to the switch. The switch then assigns a sequence number to the message and also stores the sequence along with the digest in memory. Finally, it sends the message, the digest, and the sequence number to all servers. When a server receives a message, it first checks that the digest actually matches the message. And this is important because the switch does not do that, and also clients may be Byzantine, so they may send incorrect digest values. It can then deliver bottom for every missed message, and finally it can deliver the message locally. It can also verify that a message is indeed the kth message by sending the sequence number k to the switch. The switch can then send the stored digest to the server, and the server can check that the digest matches the message. Now, VRAB is very powerful because it solves BFT in executions when there is no packet loss. Unfortunately, we assume that the network is lossy, so we do eventually have to deal with that. So again, as I mentioned earlier, we cannot retransmit messages because the switch does not store them. So in a consensus protocol, the servers have to agree on every log slot. So when a server detects it has a gap, and it can do so due to the sequence number, so you can see that it receives message number k+1, but it did not receive message number k. At that point, it can initiate the recovery protocol. In the recovery protocol, the server tries to recover the message from other servers. So it requests it from all other servers, and then if any of them sends back a message, it can verify it using VRAB. If that process succeeds, then it accepts the message and resumes operations. But if it receives at least f+1 bottom values, it stops trying the recovery process and assumes there is a NOP in that slot. However, there is a tiny issue here, and this is because we assume we basically rely on a simple majority. Some servers might be able to recover a message while others do not. And to deal with that, we rely on the switch to ensure a consistent recovery output for every sequence number. So besides storing sequence numbers and digest, the switch also maintains 2 bits per server that signify the response of the server to a recovery process. So there are 3 possible states. Either a server has not replied yet, or it has replied with a bottom value, or it replied with a message. And the switch can then ignore contradicting responses from servers. But more importantly, what it can do is once the servers reach an agreement for a specific sequence number, it locks that decision and then enforces that any following recovery process is going to end up with the same result. We also discuss further interesting parts of the protocol in the paper, for example, how we handle switch failures, how we trim the state on the switch. We provide a full proof for the protocol. We describe some optimization implementation details, and also do some scalability analysis. So I do encourage you to check out the paper if you're interested in learning more. We implement SwitchBFT using P4 on Tofino switches, and we run the client and servers on Intel machines with Intel NICs. We compare SwitchBFT against the following baselines: NOPaxos, which is a CFT replication protocol that uses the switch as a sequencer; NeoBFT that uses cryptography on the switch with an FPGA; MinBFT that uses SGX; and a few other BFT protocols that do not use trusted components. This slide shows the replication end-to-end performance, and the graph is a latency throughput graph. And as you can see in the graph, SwitchBFT achieves the same performance as NOPaxos, while the other protocols that use trusted components perform slightly worse. In the next experiment, we measure the end-to-end performance of a replicated key value store, and this graph shows the throughput that each protocol achieves. So here you can see that SwitchBFT and NOPaxos are not a bottleneck for this application. We also experimented with different message sizes and hash functions. So this graph shows the throughput against message size for different hash functions. And this graph shows that up to 256 bytes, hash overhead is negligible. And with the largest message size that we have experimented with, SwitchBFT is only 15% slower than NOPaxos. Finally, we also experimented with packet drops. So this graph shows the throughput against different packet drop probabilities. And you can see that for 0.1% packet drop, SwitchBFT almost maintains its peak performance. And at high drop rates, the performance drops by 20%. In contrast to that, NeoBFT is unable to recover some messages under high drop rates. To conclude, we believe that programmable switches are a good trust boundary for BFT systems, and SwitchBFT bridges the gap between CFT and BFT protocols by using packet source authentication and protocol verification, which enables it to provide the same performance guarantees and the same fault tolerance as the fastest CFT protocols. And this is all without signatures at all or cryptography on the switch. And with that, thank you, and I'm happy to take any questions.